And yep, here we go. Welcome to our, what month is it? March. March meeting of the Nashville Java user group. We are going to talk about data frames, which is kind of a big deal because data engineering is a big deal. Right, so you can see we have not a lot of people here today, but whoever came did the smart thing. Because data engineering today is all the rage. Phil here won't let me tell a lie about that. He's in data space and he knows how hot it is. So yeah, positive reinforcements. It's good to have you here. Our speaker, Andrus Adamchik, been around Java ecosystem forever. More or less founder of a bunch of important open source projects through Apache Foundations and more, CEO and founder of Object Style, and he's going to talk about himself soon. Your hosts, I'm Baruch, Phil that I already mentioned, Kate right here, and Evgeny. Thank you, Gradle, for awesome t-shirts. Everybody got t-shirts. Awesome stickers, swag, and what's not. Don't forget to, there is like a QR code in the bottom of there. Scan the QR code and then win more swag, basically. Thank you for the Oracle for celebrating Java community process with us. More swag, stickers, pins, whatever. Thank you, Greater Nashville Technology Council, for hosting this meetup here. Yay! O'Reilly, books. We are going to raffle books in the end. JetBrains, licenses for IntelliJ and what's not. We're going to raffle those as well. Gem.dev for pizza and drinks. And that's all. DevNexus is coming up in less than 2 weeks. April 9th to 11th. The oldest, biggest, most impressive and best conference, Java conference in the US. I'm going to be there as a speaker. Andrus is going to be, going to be there, but Evgeny is going to be here. Evgeny going to be there, Josh Long is going to be there, Venkat is going to be there, all like the bunch of amazing speakers. Check your meetup inbox. With the reminder of this meetup on Monday, I also sent a discount code, special discount code for this Java user group. If you want to go, and you should, that's what you do. You don't pay full price because you never pay full price. Job talk, I can ask who is hiring, but I guess not this year. It's been harsh. Who is looking for a job? Anyone wants to mention? Yep.
I'm looking to hire, but it has to be
Philly. So. You're looking for hire. Talk to us.
You have to be in Philly, though, so I'm sorry. Corporations are silly. I'm here, I have to hire somebody in Philadelphia.
It's a bit of commute, like a tiny bit of commute. How many days?
So beautiful nation.
How many days in the office? Full time?
4.
4, yeah, no, that's a...
No, but not really, I mean, nobody goes in 4 days.
I would say a day in a week you can fly over. More than that, it's kind of hard.
I fight with the HR people, but they don't listen to me.
So anyway.
Sorry.
Yeah, no, it's fine. Talk to Daryl. You want a little kid to Philly. No judgment.
Stay in Nashville.
Yeah, that would be weird, but no judgment. Looking for a job, Java developer.
Project manager, yeah, I found the reference.
Here you go, project manager. Yeah, you don't want to fly to Philly every day?
No.
Okay.
I was on the way to Vanderbilt University.
Okay.
It's closer to the home.
Oh yeah. Anyway, folks, talk to each other. Hopefully, we'll make it work somehow. April 25th, security. Nir Waldman, guy from Atlanta, by the way, my dear friend, he's the CEO of a company called Arnica, which does DevSecOps, like stuff, securing pipelines and this kind of stuff. Again, this is another topic that even it's not related directly to Java. I would highly recommend you to come and listen, just to broaden your horizons, and security is everybody's business, like data. So, and then May 16th we have Heather Wankura from Oracle and the Java Community Process, and the co-author of book about supercharging your developer career something, and Clay, who is a recruiter at Veiko. They're going to do two perspectives of how to basically supercharge your career as Java developers. Huh?
He's my roommate.
He's your roommate. Okay, so tell him I mentioned. Yeah. So he also hosts us at Veiko. Just today they had something else. But yeah, we did Veiko last time and it was great. Hoping to go back there. That's all for me. And now, Andrus. All right. And mute your computers.
Okay. So the mic is on, right?
Yeah, you're checking.
Oh, okay, great.
Yep.
Let me grab my mouse here. All right. Thanks for the introduction. Nice to be here in Nashville, my first time here actually. So the closest place I've ever been was Atlanta, where I lived like 20 years ago. Currently I'm in New York. And yeah, my name is Andrus, and I'll be talking about DataFrame. And the underlying question is like, how come nobody does data engineering in Java, and how to fix it? Or, I have a few other alternative names to the Swiss Army knife of Java data processing. Of course, a few words about myself, obligatory. I'm a founder of this company called Object Style, and it started back in the day to support my first Java open source project. And I was kind of on the same, even though the company, of course, we have lots of people there and they program in different languages. It probably will take a while to even list them all, but I'm still a Java developer, and I still participate and work on a number of open source projects. As you see, my GitHub profile is evergreen still to this day. And these projects are listed below. The first one is Apache Cayenne. That's the one that kind of started it all for me. It's an ORM, so if you're familiar with ORM as a concept in general, or maybe Hibernate, for instance, so we are solving the same problem. We are probably about the same age as Hibernate. We went on a little different path, so it's a different tool, but it's in the same space. It's, of course, I'm going to tell you it's nicer than Hibernate. It's, but it essentially does things differently, and this is done under the umbrella of the Apache Software Foundation. There's a sizable community, and Cayenne has been in development for like more than 20 years. It's a great tool. It's still active, and I'm using it almost daily myself. The next one is Boutique, and I know there are lots of people in Java community who like Spring Boot. It won everyone except for a small vocal minority that says it's actually it's too opinionated, too much magic there, too many annotations. So programming with annotations, and we weren't fans of that stuff back in the day, like around maybe 2016, when that space was still kind of fresh. So we decided to build like a similar thing, like a technology that allows you to write complex Java applications or simple Java applications. So essentially like the whole spectrum with dependency injection, support for modules, for centralized configuration and everything, but without a focus on magical annotations. So we still use annotations for injections, for instance, but not for the core behavior. And Boutique is also it's a project that I'm currently working on very actively. I really like how we still we're getting implementing new ideas there, and it's improving. And of course it's been in production since 2016. The next one is AgRest or AgRest, however you want to call it. How many of you know of GraphQL? Okay, everybody knows, almost everybody. So also, all these ideas, they sort of out there in the air. So like 6 months before Facebook released GraphQL, we released AgRest. We've been developing it in parallel, and the idea, of course, is the same, where your web services don't have to be fixed. They don't have to serve just like a predefined data structure. They can be an entry to your data graph, and then the client decides which parts of the graph they care about. So they can get a lot of data in one call, or they can get just a little data in one call. And you don't need to go to your backend team and ask them to implement like a new endpoint for that. And but the main difference with GraphQL is that we actually stayed within the REST constraints. We stayed within HTTP protocol. So all the interaction happens through like standard REST vocabulary, HTTP vocabulary. Get, post, put, delete, it has pluggable backends, and the default backend there is Cayenne, which essentially gives you access to a database as a JSON graph, essentially. So, and it can be thought of as out of the box. Of course, it's very configurable. You can like adapt it to anything, but by default, it's essentially a low-code solution to work with relational databases. And finally, dflib. But dflib, the rest of the presentation is about dflib, so I'll skip it for now. And let's jump to the main topic. How do we work with data in Java? So of course, this is simple things. This is just like how do we all our applications, in some way they interact with data. If there is no data, there's no need to write an application. But the way there are different types of operations that you're doing with your data, and they're represented differently. But in Java, by default, data is represented as data objects, and data objects are just regular objects. There's nothing special about them, except that they usually have very little behavior and just a bunch of properties. So they have a Java class and a list of properties. Like here, we have a product. And the product has name, color, and price properties. And for those who are not yet on Java 17 or 21 or 22, so record is essentially just it's a simplified notation for immutable data classes, essentially. So that's a class. So if you're on Java 11, for instance, or Java 8, this will be just a product class with setters and getters or a constructor for all these properties. And of course, you have data objects, and then you use collections, because data objects, they rarely come just by themselves. There's usually like a lot of them if you like fetch them from somewhere. So you use lists, sets, maps, and data objects. Okay, so we have objects, but we also have databases and many other data stores that actually store data in a different format. Is it considered data processing? So probably not. So here we're talking about a typical CRUD scenario. CRUD stands for create, read, update, delete, right? So even though the database stores data in tables, and our Java application represents data as some kind of graph like of interconnected objects, there is a simple way to get the data from the database, convert it into that graph of objects, and whenever something changes on that graph, like save it back. And this is what ORMs are for. So the main criteria here for selecting an ORM for a project is that essentially your object data is modeled very closely to your data store data, to your database data. So when there's no alter in the structure, then you can use an ORM. And this is all great, and all these technologies exist in Java, and there's nothing new about them. Data transformation, so like moving from sort of representing our data in a fixed way to data representations that actually changes. So data transformation is when you alter the structure. For instance, here's an example of the same products, like a list of products, and we would like to count each, how many products of any given color there are. I mean, it's a totally contrived example, but nonetheless. So how do we do it in Java? We create a stream, then in a stream we are converting those objects like one by one to something else, and at the end we are doing a group by, so we're doing some kind of aggregation. So that's an aggregation scenario. The thing that I want to point out here is that we started with products and we ended with something that's not products anymore. So the representation of the result of this calculation is a map of string long. So essentially color and the count. So it means that data transformation usually transforms your data structures, and in Java it's not always easy to do it. I mean, it's definitely possible, but it's not always smooth. So altering the structure when you're doing join and projection, and like, I don't know if you don't know what projection is, it's like in SQL it's essentially just your select clause, so the columns that you select from your table. So and like you can do it with a Java object, for instance, like if it has 3 properties, it has 3 properties. I mean, that's it. I mean, you can just sort of pretend that it doesn't have one and you just work with the other 2, but it is still there. So the next slide is about why Java is not flexible enough for many data transformations. First of all, the Stream API, it's very useful, of course, but it's not intended for like hardcore data transformations. There are no joins, for instance, as an example. Another thing is representing the internal states. When you actually going through a stream and you're just processing those objects like one by one, like each transformation creates some kind of intermediate object. That's not the one that you care about, but that's the one that is fed into the next step of the transformation. And at the end you get the result probably in a format that you may actually need, but all those like intermediate representations, they become like really hairy in Java really quickly. For instance, like I have this example of like map of lists of maps of sets. I know it looks kind of like made up, but very often when you actually need to like combine data from different data sources and so on, you often end up with structures like this, and they're really hard to work with and to understand and whatever. And also Java doesn't have by default doesn't have tuples, but that's probably not the point I want to spend too much time on. Now, if we pause with Java for a second and actually go to the technologies that are just pure data, so all they do is just doing like some kind of data transformations. So databases. Databases represent data. They store data in tables. So there's a hint for us that maybe table is a way to represent data. And it's not just databases. So we kind of use the databases, and we created this whole set of ORM tools to actually hide the fact that it's a table and just pretend it's an object. But of course, everyone else, like R, Python pandas, all the big data frameworks like Spark and Flink, they all are using tables or some kind of data structure that is a table really to represent data. And there has to be a reason for that. And like here I'm showing, for instance, like a simple piece of SQL that does the same thing that this stream did. Well, for one thing, it's a little more readable, but I won't say that all SQL is readable because it's not really true. But the point here is that it can focus on the data parts and just like ignore all the language abstractions and just work directly with data. So the point of this, so essentially the main point of this presentation, and I'm getting to it, step by step, is that DataFrame is a data structure that's missing from our tool set as Java developers, And there are a few open source libraries out there, but people just prefer to, I don't know, use objects essentially, not use as tables. And like I guess I'm on a mission to change that. And other people try it, so let's see how it goes. So this is a presentation of our product, for instance, as a table. And so if like our unit of operation, what we're working with, is a data frame, is that table, it actually makes lots of operations possible, or not possible. I mean, everything is possible with every language, but essentially easier and more transparent and so on. So of course there are no data frame data structure in Java, so we had to create one. So DFlib is a project that I started some years ago to actually try that, because yeah, I was envious of all the people in Python who were doing data processing and using pandas and so on. I was like, okay, so in Java it's probably we can do the same, but it's going to work faster, and we can also use it in Java applications. So it's open source. Its core is dependency free. That's another good thing about it, because there are some other data frames that have dependencies on Google Guava collections and stuff like that, which is really pollutes your application with weird stuff. And it provides a data frame and provides all the operations, and the number of operations and the number of connectors. It's constantly growing. And the next thing that I'm gonna do is I'm gonna show a demo. But before we go to the demo, let me actually mention something else. And people, of course, who are working in with data analytics and who are working in Python, they all know about Jupyter Notebook, but the Java community doesn't, or at least if they do, they ignore it. So I'm gonna use that visual environment, and again, it's totally optional. It's just this little nice thing that I wanted to show. That's yet another tool that works really well when you're doing data analytics, or doing some kind of data transformation. So what it is, it's an engine that starts a browser for you, and there you can actually write just a few lines of code in a little block and execute it, and then execute another one, and you have all those variables in memory, so you can rerun it. You can explore data essentially. So if something didn't work, you can come back and re-execute it, for instance. So it's very interactive, let's put it this way. So you can run everything that I'm going to show here in an IDE, of course, definitely, actually my advice will be if you're working on data transformation, you would start in Jupyter and then copy paste that code back into your application. If that's the end, if the end goal. But for the demo, we're going to use Jupyter. And it has this iJava kernel that actually allows to run Java code, and it has its own share of bugs, and I feel like we need to actually fork it and maybe start supporting it in DFlib. So hopefully the demo goes smoothly. All right, now the demo itself. Let me introduce the problem domains that we're going to be dealing with. One of my big clients is the National Hockey League. So I've been working with them for many years, so I know all their data, and I've been exposed to various data sets there. Here I'm going to take a fairly simple data set. It's a CSV of hockey games. I don't know, Nashville is a hockey town. I don't know if anyone is a Predators fan. Yeah. Okay. So anyways, I'm going to take a list of games, taking a snapshot, taken sometime mid-season, where some games were already played, some games were still they were on the calendar, but there were future games, and we will try to calculate team standings. So essentially, where the teams are positioned as of that date, and the demo is called ETL. So ETL stands for extract, transform, load. That's a very common term in data processing and data science, whatever, because that's how you get your data from somewhere else. And this can be within an organization. This can be external data. This can be anything really. But these processes are they usually require, if you go to a bank or to an organization like NHL, you would see a lot of infrastructure around that. So people are buying licenses for, I don't know, Talend, or even with open source like Airflow, they paying lots of money to Amazon to actually, run some clusters, some directed acyclic graphs of like jobs that depend on each other. So it's really like when somebody says ETL, it's like usually you would imagine some heavy system like distributed with different components. So the goal with the DataFrame is that if your transformation, if your ETL is simple, you don't need all that. You can just do it in any Java application, and it will work just as well as as all those big products do. So let's try to calculate some stand-ins. So we're getting, so the input is a CSV file, the output is Postgres database. So I have Postgres running here, and I have this game CSV file. That's our input. All right, and let me start Jupyter. There are a few ways to start. Jupyter Lab is one of them.
If possible, can you a little bit zoom in?
Yeah, so I will. Yeah, here we go.
Thank you.
Okay, so here's how the notebook looks like. So I already have I started it, and the good thing about notebook, you can intersperse sort of like code with some markdown, so you can actually annotate your stuff, and you can do presentations based on this and demonstrate your things. Like people do in data science, they live in those, and I don't see any reason why Java developers shouldn't. So just hit and shift enter actually executes the block, selected block. So like the first one is it's just text, so it just renders it. The second one is the only one that's kind of not standard Java, but specific to Jupyter. It's actually, believe it or not, this thing is called magic. That's a formal term. So essentially, what this one does, of course, you may have already guessed, it's you can declare dependencies that are needed by this notebook, and it loads them. And hopefully the internet works here, because they're going to be coming from Maven Central. So I do Shift Enter, and for as long as that star is on, it's downloading stuff, and everything else is Java, so just like a regular Java import. So we import in dflib. So one static import for expression. I will show them later. Okay, so it finished loading, so it's good. So I execute this guy, so that in our environment we have all these imports, and I execute the last one. And that's also, you don't copy paste that back into application, because that's just for Jupyter to know how to display DataFrame in the notebook, and the rest are going to be like copy pasting from here to save some time on typing. So the first thing we're going to do, we're going to load this game CSV, and just to be more explicit, so this var is a data frame. So that's what this is all about. And in a notebook, the last line that you enter is going to be printed. So essentially, I'm like entering this variable df1 in the bottom, so that I can see the output. So here is that CSV that is loaded, and you see it's pretty long, but it truncates it properly so that it looks pretty. So we have our games. So for our stand-ins calculation, we probably don't need all the games. We only need the games that are already finished, right? So so that we can actually get some statistics out of it. And for this, I'm going to use the game state column. And you may think that it actually contains only two states: off, which stands for official. That's actually a real data set. So all this things about how we tag our games and everything. So it's all there. And fut, of course, it's future. But there are other states, and we may actually need some of them. How do we actually tell what states there are? How do we explore this data set and just try to understand what's in there? So for this, we're gonna just take this column, so df1 get column game state, and then we apply. So this returns an object called series. So columns are series. So series are just like arrays, essentially, with a lot of good operations. And then we apply this operation value counts. It generates another data frame, but we don't care about the data frame. We just care about the fact that it has all these states there in that column. And some of them are more common. Some of them are kind of like more rare. They only happen like when the game goes from through different transitions. So for our calculation, we need official. We also need final. So the games are final, but we don't have the stats yet. So let's filter those rows. And to filter rows, we will so to filter rows, data frame, many operations on the DFlip data frame. Of course, each data frame has its own API. On a DFlip data frame, they start either with rows or columns. So we essentially select a subset of things that we want to work on, and then we decide what to do with it. Either we return that subset, or we actually merge it back to the original data frame. So there are operations that end with select, and there are operations that all end with map. So map is a merge, and select is just like give us that subset and let's show it. So here we are filtering the rows, and we applying this expression. So that's kind of like a where clause in SQL, only expressed in Java terms, and it's coming from this static import. So exp is an interface, and it has like a bunch of static methods there. And these static methods allow us to build expressions. So we pick a column, game state, and we apply this in operation. And I was talking, before the presentation that essentially, so this is targeting Java developers who are working in the IDE with like autocomplete and everything, so that it helps you to build valid expressions. But I guess for people who are doing like data analysis, we should probably create like a parser and just like allow strings, so like allow actually pieces of SQL there. That's on the roadmap. And then like we don't need all the columns here to calculate statistics. We only need we need what teams are there, and what was the score, and whether the game ended in like overtime or shootout. And I'll talk about those as well. So we only select those columns, and we get a much nicer and smaller data set that's easy to work with. And just generally, it's a good idea when you start with something like big and hairy, you just minimize it to what you need. First of all, it saves memory. Second, it's much easier to understand what's in there. So that's a data cleanup step. So now we kind of have all the numbers that we need and all the information that we need, but it's still not in the format that would allow us to calculate, for instance, the points for each team. Because here you see each row, it has both teams, and of course it has both scores. We want to do something per team. We want the team to be in a single column. So how do we do that? We just slice that data set into two parts. So like we create one data frame with away teams, one data frame with home teams, and then we vertically glue it together. And this will give us like a better data structure for our processing. Okay, that's why I have a mouse here. So you see here we're taking like this in the select, we're specifying the columns from the original data frame, and in the columns part we actually specify the desired names for these columns when we select them. And in both cases, so this is for away team, this is for the home team, we end up with compatible data frames, and then we glue them together via vconcat, vertical concatenation. So I execute that, and you see we had previously we had 764 rows. Here we have 1528, so double of that, but they're all in one column. So, and you see we are transforming our data set like step by step to get to where we want. So what's the next step here? The next step is to actually calculate some useful statistics that will help us to calculate the points. One of such things is actually goal differential. So it's like how many goals your team scored versus how many goals were scored against them. So this gives us whether the team won or lost. And another thing is over time. So over time, you see here we have different values here. We have SO, which is shootout. We have OT, which is overtime. And the way it works in hockey is there are no ties. So essentially, when 3 periods of the game end and the game is tied, they keep playing. They play overtime. And if nobody scores in overtime, it goes to shootout. So it's like, 1-on-1, essentially just, skater against goalie. And so eventually somebody wins. So there's never a tie. But the way points are assigned, it's important here. So if you win the game, no matter how you win it, you get 2 points. If you lose the game during the normal regulation time, you get 0 points. If you made it to overtime or you made it to shootout, even if you lost, you get 1 point. So we have all these 3 states and we need to calculate them. An overtime column is going to help us. So let's actually calculate goal differential and figure out and prepare overtime for the calculation. So we're not calculating points just yet, but we are still massaging our data set. So I'm adding 2 new columns, or rather I'm defining like a transformation on 2 new columns. One of them is an existing one, so it's going to get overridden, and one is a new one, it's going to get added. And instead of select, I'm doing map. And map essentially, it's like, okay, so work with this column set, and once it's done, merge it back to the original data frame. So the result is a data frame, and the overtime it's calculated essentially from a string. I just check if it's blank, then it's not overtime. If it's not blank, then it is overtime. So converting a string to Boolean, that's going to help us in the next steps. And with the goal differential, I am taking the scores, and the score is taken as a string. Why is it a string? Because data came from CSV, and in CSV everything is a string. And of course, until we explicitly convert it to something, it's going to stay as a string. So here we know that it's really an int, so we convert it to an int, and then we subtract another column, also convert it to an int. So we're doing this. Okay, we have goal differential, so some are negative, some are positive. So somebody won, somebody lost. Overtimes are Boolean now. So now it's actually ready to. It's ready for points calculation, because points is the main criteria for standings. So points calculation is the same thing. So I'm taking a column set with a new column points and provide an expression to generate that column. And here it's like a nested if expression. So if goal differential bigger than 0, then you get 2 points. If not, we check for overtime, and you either get 1 point or you get 0 points. So, I don't know, can you see it like this? Okay. I guess one new thing here is this value expressions, because these expressions, they are not just simple functions. They actually they're functions that work on an entire column. So you can actually implement something like array optimized, for instance. So this is why they're not just operating on values; they're operating on arrays. And here, if I have a constant, if I have 0 points or 2 points, and I want to generate an array out of that, so I'm using this special expression val. So essentially, it's a constant value that this is going to go into every cell of the array. So let's. Run this, and now we also have points. So we came to a place where we can actually aggregate things, and aggregation is actually a multi-step process. I'll probably just take it one by one, and this is where Jupyter is great. So if I can just run individual pieces and then enhance it line by line. So first we're going to do aggregation. So we're doing group, just like in SQL, group by. We're grouping by team code. And then we need to produce a result, aggregated result. So for the first column of the aggregated result is the team itself. Since within a group all teams are the same, all team codes, I can just pick any one of them. So I'm picking the first one within a group. And for points, we're going to create a sum. Goal differential, we're going to create a sum. And we also need this little new thing. It's also used in the calculation, how many games are played, because that's important when there's you have the same number of points. We need to decide who goes on top. And also, like each columns can be renamed right in the expression. So kind of like in SQL, you can do a column as this. So expression also can have this as this. So let's run this. Oh, we forgot to print the data frame. So instead of like whatever, like 15, oops, I don't want to do that. Instead of 1,528 rows, we got 32 rows, which happens to be the number of teams at the NHL currently, and so each one of them has points, has goal differential, has game played. So the next step here, so let's start on commenting those things, is to actually sort in the order they should be in the standings. And the first criteria is points, and you see the same expression, but then the expression produces a sorter. So you can take a bunch of columns and then say, okay, sort by that expression. Not necessarily a column, it can be some derivative, but here it's just a column. So descending by points. If teams have the same number of points, we then sort by games played. If you played fewer games, you go on top because you have a chance to get more points in the following games. And finally, if everything was equal, goal differential is the last criteria. So we run this, and finally things are sorted. So like we have Boston on top with 71 points. We have Vancouver and Colorado with 67 points. But Colorado played more games, so it goes in the bottom. So that's already our standings, but we also need to assign them like explicit numbers so that people don't need to resort it every time. So we also add an extra column, and this row number it's an expression also. It's an expression that actually essentially when it's applied to a column, it just generates numbers 1, 2, 3, 4, 5, 6, 7, and so on. And so that's going to be our rank. So that's our standings rank. So we just succeeded with extract. This was the first line. Transform part of the ETL. So the transformation, of course, it's more complex. Now we are left with one last piece, which is load. So we are loading that to Postgres. And in Postgres, like I already, okay, and hopefully I can also increase this. I have this one table, it's empty. It exactly matches the data frame. And the good thing about like versus ORM, for instance, like with data frames is that you don't need to do any upfront modeling. You can save the data frame to any table really. So you just decide when you save it, you decide which table it goes to. So like today it can go to this table, tomorrow it can go to some temporary table. You won't be able to do it with ORM where everything is already predetermined. But I have the standings table, and the only requirement is that the columns, the labels in the data frame, they match the column names, and they happen to be exactly the same. But if they are not, renaming the columns is a very cheap operation. So data frames, remember, they are column and data structure. So, we just reassign the labels to the columns, and everything should be good. So how do we save to the database? It's just a little more complicated than reading from a CSV, but but not by much. So we need to create this connector that connects to the local Postgres, and then we can use this connector object to do any database operations. So the connector itself prints just like this because it's nothing interesting. So now we're saving our data frame. So we create this, we go to connector, say, okay, give us an object to save to a table called standings, and then just save our df. And you see there's some minimal autocomplete in Jupyter. It's kind of primitive, but it still works. And now we save it. So it printed some SQL in the logs, and the important part, it printed some statistics. So it inserted 32 rows. And we can actually go here and I'll increase the size shortly. Execute. Okay, so we have our standings in a database. So our first run of the ETL succeeded end to end, right? So we got data from somewhere, we transformed it, we loaded it. How is it different from the real ETL? Is that the real ETL actually happens periodically. So this CSV file is gonna keep coming. It will come to you every day or every minute or every second. During the games, it actually, it may come like very, very often because the games are played, we immediately want to change the standings. So if something changes in the file, so how do we update it? So let's actually fake it a little bit. So here, remember that, like for instance, Vancouver was in second place, and we're gonna find like a Vancouver game, and actually flip their win, change it into a loss. It's not fair. Okay, so let's assume that's our new CSV that came with like different data. Maybe the stats got updated or something. We can re-execute it here and actually see what happens. So I'm starting at this step, and I'm just running all the steps one by one. And here you see Vancouver got pushed to the 5th place because one of the wins got changed to a loss. Connector is already there. I don't need to rerun it. But what happens if we save this? So if we save this again, what's going to happen is going to create another 32 rows, and every time you save, the table is going to grow, and that's probably not what we want for a standings table, because that's just sort of a snapshot in time. We don't have a date, so it has to be current. And for this, we can be a little smarter about our save step, load step, and we can actually do a merge. So you can merge by multiple columns. In our case, just one team. And when I run it, you see it printed that it updated only 6 rows and unchanged 26 rows. And this is actually pretty neat because I've seen many even like big organizations, like really Fortune 500 companies, where the ETL usually goes like delete from table without a where clause, and then insert, because it's easier. Of course, we want easy. But if you actually want this data to be there, and don't disappear suddenly and reappear, and you can have like millions of rows, you actually want a smart merge, and like dflip, for instance, will do it for you for if there are some columns that we can compare. And you see it does a select first, and then it does in-memory comparisons. It's not we cannot see here, and it compares and creates this delta, and from that delta it generates the statements that are needed. So it will generate inserts or updates. So it's very it pinpoints the changes and just saves those. And I guess it's just my background with ORMs, where I actually like SQL generation, so I worked a lot on this piece. So now if we go back here and re-execute this query, so you see Vancouver got pushed to the 5th place, and there's only 32 rows, there's nothing else there. So this is our demo. So we were able to take some data, clean it up, first of all analyze, understand what's in there, then clean it up, massage it a little bit, restructure it, and then save to a database. And now we can actually copy paste this code to our applications that's going to run somewhere in the cron, or all without paying Amazon for a Flink cluster and streaming and stuff. Okay, and I know it's actually pretty bad for resume-driven development, because people actually want to have all those Amazon tools on their resume. So sorry about that. So, okay, going back to the slides. Okay, so we have all those choices. So I just wanted to maybe discuss a little bit where the DataFrame concept fits in a normal Java developer flow. So on the one hand, we have object streams, we have ORM, On the other hand, we have big data, and of course we have SQL because you can process data in SQL and not even bother about with like Java and all that. So I'm just listing some hints, and they're not they're not going to cover every single scenario, but at least that's some roadmap a little bit. So CRUD, of course, when there's non-minimal transformation of your object data structures, and use ORM because that's great, and objects are nice, they're compile time checked, and all that. When your transformations are simple, use Java streams. Java streams are great for simple transformations. When the data is already in the database, don't take it out. Just do all the data work right there in the database. Data locality is one of the sort of fundamentals for like big data, because if you don't respect it, if you actually like move your data around just because you want to calculate an aggregation somewhere else, you're in trouble essentially. Your system is going to be slow and inefficient. So if your data is in database, just stay there. And the final point is when you actually move to big data, when you actually are ready to pay Amazon for the cluster. So this is when you have like really big data sets that don't fit in memory, and there is no easy way to partition them, because even big data sets you can actually like process them one chunk at a time in memory. But if you can't, just let Spark or Flink partition that for you, and just do this magic that they're famous for. But on the other hand, this is a criteria, so we sort of like went from the negative criteria where you don't need to use DataFrame. So here is where you might want to use DataFrame in addition to those. So first of all, data fits in the app memory, because DataFrame is complete. It's an in-memory structure. So if it doesn't fit, you would either partition it or just go to big data. If you actually write in the Java code, you write in your own transformations with streams, and suddenly you end up with this data structure, this scary list of set. That's a good indicator that maybe that's a task for a DataFrame. Then the next one is similar. When you implement custom joins and group by, and I've done a lot of that. So when you actually before you can actually start a stream, you start another stream and create a map of something to something, and then when you go to a stream, through a stream, you look in this map and try to find a matching object for your stream object. This means that you're probably should be using something else, like you're reinventing basic algorithms. Of course, it's very easy to use DataFrame when your data sources or data targets are already tabular. So if you can definitely convert JSON to a DataFrame. Of course you can, but it's a bit of work, and it's not always natural, because JSON, just like Java objects, they are hierarchical. They're graphs, trees, or whatnot. So they're not flat data structures. So you'll need to flatten it somehow. If your data is already a CSV or a database table or an Excel, then it's going to be very easy for you. It's going to be this little, almost one-liner, but I guess in the real case it's still more complex. But very simple way to acquire this data and get it in memory, and then start doing all those transformations. Another good thing about DataFrame is that it's not connected to anything. So it's not connected to an open to an open database connection or some kind of session or whatever. It's a pure in-memory object, just like a list or a map. So if you have a mix of data sources, so some data comes from here, some data comes from there, try joining them with an ORM. You can't. But with data frames, you get both of 3, 5 data frames, however many you need, and then you can just work with them regardless of where they came from. It doesn't really matter. So once it's a data frame, it's just a bunch of values. So I think it's a fairly compelling set of use cases where standard Java approaches, they work, but they're not ideal. So this one makes it better. some examples on top of that, so like where we actually use that. So data exploration, like we saw it in the demo, where we can actually, before we even do anything with the data, we just check what's in there. So what type of data, like what type of values you can see that. Like another one, I like that ad hoc log analysis, because many organizations, I mean, they invest like really like they're paying for like Splunk licenses, and like it's all like expensive and fancy and like great because you need to collect the logs from all your applications from everywhere in one place. But then when you start querying it, again, like maybe I was unlucky, but the few systems that I worked with, they collect the data, but like from there, it's just getting something out of this log streams is like next to impossible. Like getting some intelligence, understanding of like why your application is failing, for instance, or it's not performing well. So what I do is like I go to that fancy system, like use their whatever REST API for CSV export. I get a CSV. And I drop into Jupyter and actually try to figure out what's going on. And of course, the downside of that is that my 16 gigabyte laptop is, can't fit a lot of logs in there. And something that I haven't shown here is you can actually do charts, in Jupyter also. So you can actually like, visualize your trends with DataFrame, and that's also sort of like. A rapidly developing area in DFleep where we want to better integrate with charting packages, or you can do it now, but you need to jump through hoops. And of course, if your users are uploading Excel files, you're dealing with like expense reports or accounting or something, and like some business users. Actually, some people they want to model their processes in Excel, and then like, they don't want to use your API or rather UI that you build that is pretty and like nice to use. They still want to offload your data into an Excel, then just work on it and then load it back. So I've seen plenty of those, and like this is where having DataFrame is golden. And finally, no drama ETL. This is what we saw in the demo, where instead of provisioning a cluster of talent and doing like some talent model with all the jobs that depend on each other and everything. We just did a little bit of Java hacking, and we can put it in our application. It can even be in the regular applications that serves like REST requests. In the background it runs also like this ETL job. So it's up to you. It's how you architecture it. I have like a little call to action below, because DataFrame, like I really think it deserves like a little more, spotlight in the Java community. So if you can think of cases where your current approach with like Java streams or something, like it's not really the best way to solve it, but and you have a specific case, share it with us. Let's actually add it to our list of use cases. So you can go to our GitHub project, for instance, and under discussions, just mention it. So I think that's how we may start a community around that. Okay, so I'm wrapping up here with some conclusions. So DataFrame is a Swiss Army knife of data processing, in the sense that it has all these nice data operations that are not found elsewhere in standard Java APIs, and we are adding to that list almost like weekly, monthly. It doesn't require any special infrastructure. It's just an object, just like a list or a map. So you can just start using it in your app without much commitment. So you don't need to take a course or ask your DevOps team to provision some servers. You can just start using it. It is like SQL functionally, so like you would find like lots of analogies with SQL, and for those who use pandas, of course, you'll find analogies with pandas, but I think SQL is sort of like a least common denominator here. But unlike SQL, it's actually composable, so you don't need to write everything in one statement. You can actually do these transformations like step by step, like we did in the demo, and it means that I mean, it may actually look as, writing more code than needed, but the upside is that you can actually see the intermediate results, so you can actually see what happened at each step, and you can debug it, you can write tests for your methods and so on. So each transformation you can write unit tests. It's not a replacement of anything. So it's, all those technologies, I'm not saying they are not needed they're definitely, they have their place and we all love and use them. ORM, SQL, streams, whatnot, but this is a complementary technology, so it fills a gap that sometimes we're oblivious to this gap, but it exists. And of course, there are some, okay, so there are some links, so dflib links, the site, GitHub, Jupyter, but Jupyter actually, the last link, maybe the easiest one to get started is dflib documentation. We actually have like a chapter on Jupyter, but for now only for Mac, so just install it with Homebrew and so on. Because you need to install the custom kernel, so it's essentially there's a few hoops to jump through. Yeah, I will try my best and like with our team to actually fix all the bugs in the iJava kernel. And of course, like another call to action, if you can go to GitHub and give us a star, that's much appreciated. Only if you liked what you saw, of course. So that's it. Thank you. So, any questions about dflib, DataFrames? Yeah.
Yeah, a few questions. How large of a data set have you ever worked with this tool?
How long, sorry?
What's the largest data set?
Oh, it's a large data set. It's constrained by your machine memory, essentially. So like on my 16 gigabytes, the data sets that are logs, so essentially it's not just integers, it's like long strings. I can probably process, I don't know, like 10 million rows. But that's, of course, it depends on like the widths and like and everything.
How performant would it be considering that large?
It's actually, it is comparable, again, like we have some benchmarks, but like we have internal benchmarks, so essentially we compare like, previous version with the current version so that, we don't make it slower, we actually make it faster. But I did some comparison, of course, it's much faster than pandas. It is comparable with Spark on the same hardware. Of course, Spark can scale out infinitely, but within a single machine it's comparable. But unfortunately, right, it's a bit of like comparing apples to oranges, because, like, for instance, they will have a faster algorithm to load a CSV, but slower like column map like algorithm, and ours will be vice versa. So essentially, it really depends on what you're doing. But I guess the point is that it's comparable to everything else, and I don't think we hit our essential performance limits. I don't know if you heard of 1 billion rows contest. That just happened recently, where people were processing like 1 billion rows, and it's not a use case for DataFrame, because essentially they're aggregating on the fly, so they're not creating an intermediate data structure. But what I took from that is that you can actually load a multi-gigabyte CSV, and you don't need to do it linearly. You can actually memory map the file and just load it like in parallel in chunks. And that's on the roadmap as well. So essentially, we're improving all that, and we are parallelizing more and more things in like right now. Aggregation is all in parallel, so each column is calculated by its own core, and we optimize in memory, and like actually, memory uses much better than objects, of course, because those are arrays. So like array of integers is it takes much less memory than like if you have an object and with an int field. So this stuff is optimized. There are vector optimizations that we actually we're not using like the explicit, like the new whatever JEP vector API for. In Java, but Java Hotspot does a good job if you write the code in a certain way. It optimizes for CPU vector extensions, essentially. So things become faster because they're calculated again as arrays. So the atomic operation becomes an operation on the entire array instead of just individual values. So we've also seen certain things like they became like, I don't know, 40% faster as a result. But that's like little things here and there, and that's a constant work, you know, to make it more efficient.
Andrus, what are the main limitations you would like to highlight for running and using that library?
The first one is the amount of memory that you have. So if it doesn't fit in memory, you know, it's not going to work.
In terms of functionality?
Oh, in terms of functionality, it's a good question. So it's I think we cover like pretty well. You know, all the main functions like, you know, group by, window functions, all kinds of joins. Of course, you know, the regular filtering and like this and this direction. There will be some gaps here and there, but I don't think we are missing like any major pieces of functionality. So essentially, it's I guess the expression API doesn't have everything as an expression. So essentially, as this vector operation, but instead, when some operation is missing, there's this like, you know, fallback where you can actually write your own lambda. So you just say, okay, this transformation is not available in standard expression API, but you know, I can do it myself, and so you just plug it in there, and so.
Can I read multiple CSV files, let's say?
Of course. Yeah.
And there is no any concurrency issues.
Oh, concurrency is an interesting topic. Like I didn't have time to include it in the presentation, but I'll be happy to mention. Data frames, series, index, like all the parts of the data frame, they're all immutable. So whenever you make a change, a new data frame is created. And of course, because they're immutable, I reuse like everything. Like if you add a column, you know, all the columns are reused. I just add another column and create another data frame. So you don't see that we are like sharing the data. So there are no concurrency issues at all. So it's unlike pandas where, you know, I think you just operating on the, you know, on the same memory. I had some concerns about performance with this, but I don't see any really, because like real operations, they I don't.
It's meaning
Yeah.
that if I wanted to use merge for update, in our case, some CSV file, can I use merge for different modes? One of them for append, another one for write. Is it possible to use with your library?
So for what operation again?
Merge with mode for writing.
Merge.
And overwrite.
You mean on a data frame or on a CSV or okay? So,
I wanted to drop my all prepared data frame in CSV file, and I wanted to use a specific case scenarios. Some of them I want to update. Some of them I want to.
oh, you mean so essentially update the existing CSV file. So on CSV, so everything I said about immutability, of course, it pertains to the data structure in memory. On CSV files, right now we don't have an API that will actually like override a part of it. So it's always a new file.
Okay.
So, but again, like this is why I'm asking about use cases.
Yeah.
So send them my way. Yeah. Right.
And it's a support as well, pure without Jupyter notebook as well, right? So I can build with Maven.
Yeah, so it is like DFlib itself is like, you know, using Maven internally, and Jupyter is just, you know, for visual exploration. It's just another environment. But of course, you know, we use it in IntelliJ normally, so that's where things are. So Jupyter is just for exploration and to copy back the code into IDEA. Yeah.
Thank you.
Yeah.
So you mentioned that one of the constraints is memory.
Yeah.
That you have. And you also talked about reading multiple files. I'm guessing if you were reading multiple files, you would need the memory to have all of those files.
Yes, of course. Yeah. Or you will need to devise some, you know, clever algorithm where you just like process them one by one and just like do them sequentially and then throw them away. Yeah.
You said it's impossible to work with JSON files, reading them into the data frame.
No, it is.
Because they are complex structure. I remember I did that with even embedded collections.
Impossible to do what? Sorry.
JSON file with
Oh, JSON.
complex structure. I want to build data set.
No, we have we do have a connector for like reading JSON, for instance, but I'm just saying that it's not natural. It's possible, but it's if JSON. I mean, of course, you know, if your JSON is just like one level deep, just objects with properties, then there's no problem.
No, I'm talking about autocomplete.
Yeah, so yeah, it is possible, and like we have, I think we're using something like JSON pass to flatten the properties of a tree to columns. But you need to essentially model the transformation.
So it's not like Spark working?
I don't know everything about Spark, so I can't compare this particular piece. But maybe, yeah, maybe I should take a look, because yeah, with JSON right now you need to model with like JSON pass, essentially, you know, where to find the value for that column. Yeah. Or of course, you know, you can read the entire tree as like some JSON object and put it in a single cell too. Okay.
There is no folder functions in documentations.
Folder?
Flat function. That's mentioned about JSON entire elements when I wanted to just tweet and use like simple columns when I have child elements.
Again, you can, but you'll need to specify those like JSON pass expressions.
Okay.
Yeah. So and I think JSON is one of the places where we can improve the model, because yeah, I guess the use cases that we were dealing with, we didn't have like this like deeply nested JSON structures that we cared about. So like yeah, we need to plug that hole.
I actually do have one more question.
Sure.
So you mentioned that basically with DataFrame, you can write to a different table, which is a limit of DataFrame.
Yeah.
I'm guessing the answer is yes, but is there like error handling for if the table like columns don't add up with what you've
Yeah, you'll get a JDBC exception essentially. You'll get an exception from the database.
Right. That's okay.
Yeah. So we're not going to check it, but the database definitely will.
Yeah. Okay.
So what we do is like we generate an insert statement or an update statement with the column names, and of course, you know, if that statement is not recognized by the database.
Okay. And we could do error handling around that too.
Yes, of course. Yes, you can do like try catch, or yeah, if you're really like schema is like kind of dynamic and you can't guarantee like certain schema, definitely. But to me, again, like, you know, coming from the ORM world, the great thing is that, you know, I can actually, like, you know, decide. I can use temporary tables. I can decide on the fly which table, you know, I need for the source as a target. Okay. More questions? All right. Thank you, everybody.